Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Last video we started talking about different applications of our energy principles, and today we're going to build up on that. So if you haven't watched the last video, go watch it now so that you can understand every explanation. Today we will start with a very easy example and solve it with Newton's law. Then we will try and solve it with energy principles, and it will prove much faster. After that, we will use energy principles in an example that could be impossible to solve using Newton's law, or could be really hard. That way you could understand how powerful these energy principles really are. So let's start! For our Newton's laws example, imagine we have a mass, m, falling at free fall with gravity g and at a height h. Now, we know from Newton's law F equals ma, and in this case the force equals mg minus mg. In the j-hat direction and in the j-hat direction, but we can cancel those, and also the masses. So we find that acceleration, which is the derivative of velocity, dv dt, equals minus g. In this exercise, what we aim to find is the velocity at which the object hits the ground. We see that we have to go from our initial velocity v0 to final velocity v. dv equals minus g dt, going from 0 to t. We will assume for simplicity that this initial velocity is equal to 0. That way we find that velocity equals to minus gt. But now we still need to know how much time does it take for this object to cover this distance h. To do so, we need to carry out integration one more time. We defined this velocity as dx dt in one of our first videos, and we have this equal to minus gt. Therefore, by solving for dx and integrating from h to 0, from our initial height to our final height, we find this is from 0 to t minus gt dt. We end up getting that 0 minus h is equal to minus g t squared over 2. By solving for t with these positive signs that cancel, we get that, I'll write it over here, t equals 2 times h over g and the square root. We can easily check that this has the appropriate units, as this is meters and this is meters over second squared. So the meters cancel and we get seconds on the top with the square root. Now we need to substitute this expression for here, and we get that the velocity equals minus g times our value for the time, which is 2h g. This is equal to g to the power of 1/2, so we would get minus 2h g. And it has been a fairly long and complicated process for the easy problem we had. Now let's try and solve this problem using energy principles. We know that the non-conservative work is going to be, that's not a W, the non-conservative work is going to be 0. because we're going to ignore air friction once again. Therefore, we know that the change in kinetic energy plus the change in potential energy equals 0. Now, we just need to define our energies for the initial position and our energies for the final position. We know that at the initial position, Ki equals 0, because we said the initial velocity was 0. We know that the initial potential energy is going to be mgh, as we found in the last video of potential energy. We know that this is the unknown we are trying to find. It's expressed in terms of the velocity, so we don't really know it yet. And the final potential energy is going to be 0. Therefore, substituting all of this in here, we find that K final minus K initial plus U final minus U initial equals 0. We see that these and these terms are 0, and we find that K final equals U initial. Therefore, 1/2 mb times the velocity square equals mg8. We can cancel the masses, and we easily get that the final velocity is equal to √2 g8. The exact same result we got earlier, but in a much more easy and faster way. Great, now let's try and solve this problem using our energy principles, which will be impossible to solve with Newton's laws, or at least it would take you loads and lots of time. We start with a mass over here that is at a plane inclined in such a way, at a frictionless surface, such that all of this potential energy is converted into kinetic energy. Then we'll go through a friction, an area with friction that has a changing friction constant. And after that, we will reach a spring. And this spring is going to contract once we hit it. The objective is to find how much will that spring contract. So we are trying to find, once this mass gets over here, how much will the spring contract. We see that there's 3 very differentiated regions in this process, or in this race that our mass is going through. We first have one that will have a very important role of gravity and potential energy of gravitation. Now we will have a zone in which mechanical energy is not going to be conserved, as friction is a non-conservative force. And after that, we'll have a new zone where friction doesn't work anymore, and we will have to find an equivalence between the kinetic energy that it has when it enters this section and the potential energy that it has once it reaches the final position. So let's start with it. The first part, we're going to define our 0 point of energy over here at U energy y equals 0 equals 0. Therefore, we know that the initial potential energy of our object, Ui, is going to be equal to mg8. Now, it's going to go through this plane. However, note that the normal force, that is the one that's going to make it turn, always points in this direction, points in a direction perpendicular to movement. So, as we know from our first video on work, we know that that is not going to make any work. That force is not going to affect nor the kinetic energy nor the potential energy. It's going to transform over here. Therefore, as it is falling, the potential energy is being transformed into kinetic energy. And this slope helps it become kinetic energy in this direction as it is frictionless. So, at this point, we know that the change in mechanical energy has been 0. Therefore, the change in potential energy equals plus the change in kinetic energy equals 0, and the change in kinetic energy equals minus the change in potential energy. We have lost all of this potential energy, so the change is minus mg8, and we had no initial kinetic energy, so final kinetic energy equals mg8. We can easily see that our final velocity, 1/2 mv final square, this is actually the same thing we did earlier, times equals mg8. We can find our velocity if we would like to. But this would not be relevant, it's just out of curiosity. Now, we're going to go through this zone in which there's going to be a non-conservative work. So that will be equal to the change in kinetic energy. We know that work non-conservative equals the integral from x equals 0 in this case to x equals d of the force, which is the friction force. In this case, it's going to be the coefficient of friction, which we will expand on that, times the normal force, which is no other thing in this case than the weight, so mg. Now if we expand this expression, it's from 0 to d of u0 plus u1x times mg dx and dx. So we can easily solve this, and we find it is equal to mu0 times d plus mu1 d squared over 2, all of it multiplied by mg. And this is the change in kinetic energy, well, in mechanical energy that we experience, and it's going to be negative, sorry about that. So we're going to lose some kinetic energy in this process. Our final kinetic energy is going to be, let's call it kf prime at this point. It's going to be equal to that initial kinetic energy we had over here before entering this friction path minus mu0 d mg minus mu1 d squared over 2 mg. Now, we know that in this last section over here, energy is going to be conserved because there's nothing doing some non-conservative force. So, this kinetic energy has to be equal to the final potential energy once this has reached 0 kinetic energy at the farthest point it's going to reach. So this is going to be equal, the final kinetic energy, it's going to be equal to U final. They have to be the same, by the same reasoning we made over here. Therefore, we find this is equal to 1/2 kx squared final. And if we want to solve for x final square, we see we get x final equals 2 over k, it's the square root of all of this mg8 minus mu0 d mg minus mu0 1 d squared over 2 mg. And that is not a very good mu, so let's change it. And I think we can all agree that it would have been much more complicated to reach that answer using Newton's laws than using energy principles. That is all for today. I hope you really got to appreciate how powerful these energy principles really are. Now, I hope that when you encounter a physics problems, you are willing to use energy principles and try to find the easy ways to solve it. Because this is an example of what we've been talking before in some videos. If you start working and doing a very hard work on it and try to solve this with Newton's laws, you're going to get nowhere. But if you think about it and then realize that energy principles is a much more easier way to go, you can apply them and get to the answer in half a page instead of 10 of them. So, any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button and the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!